basis of a vector space. Let V be a vector space over the field we denote by K, the field of real numbers, or K, the field of complex numbers. Definition. First definition number 1. A subset W, a subset of V is a subspace is called a vector subspace of V if the following condition is satisfied. If for X and Y from W and alpha beta scalars from K, it follows that alpha X plus beta Y is in W. This condition is equivalent to the following one. For X and Y from W, X plus Y is also in W, and the second condition here, for X from W and alpha, a scalar, alpha X is in W. So when we have to prove that a subset of V is a subspace, we can use one of these two equivalent conditions. Let us denote this by 1, this by 2. It is almost evident that they are equivalent. From 1, it follows 2. If we accept that this condition is satisfied, then for X, Y from W, we get X plus Y. Here, evidently, 1 is in the field of scalars. If we, this can considered as the combination 1 times X plus 1 times Y, and this will be a vector from V. And for the second condition, if for X from W and alpha from K, from this we get that alpha X, which has this form, is alpha X plus 0 multiplied by a certain vector. This is in W. From 2, if we accept that these conditions are satisfied, then from this it follows that this condition is also satisfied. Let us start for X, Y from W and alpha beta scalars. By using the second relation, we get that alpha X will be in W, and beta Y will be in W, and we use now the first condition. From this we get alpha X plus beta Y will be in W. So these two conditions are equivalent, and in this case we say that the subset W of V is a subspace. Now the following result. If S is a set of vectors V1, V2 up to Vn from our vector space, then the following set span of S equals is the set of all the linear combinations of these vectors alpha 1 v1 plus so on plus alpha n vn, where the coefficients alpha k are from the field of scalars. This is a subspace of V. Proof. We use, for example, this formulation of our definition. If we take two elements of this set, for if alpha v1 plus so on plus alpha n vn is this evidently is an element of span of S, and a second element, beta alpha 1 here, beta 1 v1 plus beta n vn. Then the addition, we have to prove that the sum of two elements, which can be written, if we add this, there is the obtained vector can be written as alpha 1 plus beta 1 v1 plus so on up to alpha n plus beta n vn. This is the sum, and you can see that this vector belongs to span S as this form. For a vector from span of S, that is for such an element, alpha 1 v1 plus alpha n vn from span of S, and a scalar alpha from the field of scalars. From this we get that if we multiply this by alpha by using the rules of computation in a vector space, the product can be written as, let us use here a different lambda. We have already used alpha. Lambda alpha 1 v1 plus so on plus lambda alpha n vn. This vector has this form, so it belongs to span of S. So these two conditions are satisfied, and hence this subset of our vector space V is a subspace. A definition number 2. We say that S, a set of vectors from V, S V1, V2 up to Vn, is a spanning set if or also we can say that S spans V if V is exactly the span of S, that is, if V is the set of all the linear combinations of these vectors alpha 1 V1 plus up to alpha n Vn with coefficients alpha k from the field of scalars. Spanning set for our vector space, or we can also say that S spans V. S spans V. Now the third definition, we say that V is a finite dimensional vector space if there exists a set of vectors, a subset, there exists a finite set of vectors S in V such that V is span of S. In this case, we say that our vector space is a finite dimensional space. Now an example. Firstly, prove that W, the set of all the vectors x1, x2, x3 from R3 satisfying the condition x1 plus x2 plus x3 equals 0 is a subspace of R3 with the usual structure of vector space, and B, find a spanning set for the considered subspace. Solution. Firstly, in order to prove that W is a subspace, we use the definition. Let us consider firstly two elements if x1, x2, x3 is from W, and the second y1, y2, y3, also another vector. This is equivalent. From this we get a condition that these numbers satisfy this condition: x1 plus x2 plus x3 is 0, and this vector also is from W, so W1 plus W2 plus W3 is also 0. If we add these two equalities, we get x1 plus y1 plus x2 plus y2 plus x3 plus y3 equals 0, and from this relation it follows that the sum of the two vectors, let us call the first vector to be x, this a short notation for the second vector y. From this we get that x plus y, the usual structure of vector space. This vector we have to add by components. X1 plus y1 is the first component. The second component x2 plus y2, x3 plus y3. This sum belongs to W, and we have also to prove that for any element, any vector from W, if we multiply it by a scalar, we get also a vector from W. If x equals x1, x2, x3 is a vector from W, and alpha is, in this case, the field of scalar is the field of real numbers. The usual structure of vector space, real vector space R3. From this we get the condition to belong to W is x1 plus x2 plus x3 is 0. If we multiply this relation by alpha, then we get that alpha x1 plus alpha x2 plus alpha x3 is also 0. And from this we get that alpha x, which is alpha x1, alpha x2, alpha x3 is an element of W. So W is a subspace of R3. Now we have to identify a spanning set. For this, let us start from the definition of W. Definition of W. The definition can be written from this relation. We can express x3 in terms of x1 and x2. So an arbitrary vector will have the form x1, x2, and instead of x3, we can write minus x1 minus x2. Now we have two parameters, x1, x2, real numbers, arbitrary real numbers, and this vector can be written as x1 times 1, 0, minus 1 plus x2 times the vector 0, 1, minus 1, where x1 and x2 are arbitrary real numbers. And this means exactly that W is the span of the set of vectors V1 equals 1, 0, minus 1, and V2 equals 0, 1, minus 1. So we have identified a spanning set for our subspace. Now another definition. Linearly independent system of vectors. Then we'll define the notion of basis of our vector space, of a vector space V. But firstly, the following definition. Definition number 3, I think. we say that S, the subset of vectors v1, v2, vn from the considered vector space is linearly independent system of vectors if the following condition is satisfied. An equality of the form alpha 1 v1, a linear combination of these vectors, sum up to alpha n vn. This can be 0 if only in the case when all the coefficients alpha 1 equals alpha 2 equals so on equals alpha n are 0. But this condition is equivalent to the following one. None of the vectors of S is a linear combination of the other vectors. These two conditions are equivalent. Let's thus call this condition number 3, number 4 here. If these equivalent conditions are satisfied, then we say that our system of vectors is a linearly independent system. The vectors are linearly independent. Firstly, let us show that from 3, if 3 is satisfied, then 4 is also satisfied. We accept that this condition is satisfied, and for example, V1 is not a linear combination of V2 up to Vn. Since in the opposite case, V1 equals beta V2 plus so on plus beta 2 plus beta n Vn. In this case, this relation can be written as 1 V1 minus beta 2 V2 minus so on minus beta n Vn equals 0. But we assume that this condition is satisfied, and such a relation we know that it is possible only in the case when all the coefficients are 0. This is impossible. By accepting 3, then from this relation particularly we get that 1 must be equal to 0. So, evidently this is not true. Similarly, V2 is not a linear combination of the other vectors. In a very, very similar way, we can prove that V2 and also for V3 and so on. So none of the vectors of this set is a linear combination of the other vectors when we accept that this condition is satisfied. Now, let us prove that from if we accept this condition, then it is necessary to have also satisfied this condition. So from 4 it follows 3. For this we accept 4 and we start with such a combination. Let us consider a linear combination of our vectors equal to 0, alpha n Vn equal 0. And we have to prove that all the coefficients must be 0. Firstly, we have that alpha 1 is 0, since in the opposite case, alpha 1 different from 0, this condition allows us to express V1. V1 is minus alpha 2 over alpha 1. We can divide this is different from 0, V2 minus so on up to alpha n over alpha 1 Vn. So, but this is not possible. We accepted that 4 is satisfied. Similarly, alpha 2 must be 0, and so on up to alpha n must be 0. So these two conditions are equivalent, and in this case we say that our system of vectors is linearly independent. As an example, let us prove that the obtained spanning set for in the considered example is a linearly independent system. As an exercise, prove that we have obtained the system of vectors V1 equals 1, 0, minus 1, V2 equals 0, 1, minus 1. This is a linearly independent system of vectors solution. For this, we consider a linear combination by using the definition. Let us consider a linear combination. Alpha 1, we have just two vectors, V1 plus alpha 2, V2 to be 0. If we substitute here, alpha 1, 1, 0, minus 1, plus alpha 2, 0, 1, minus 1 is 0. Here is the null vector from R3. That is, we denote the null vector symbolically by 0, but in this case it is this vector, so 0, 0, 0. Now if we compute here, we'll get firstly the multiplication alpha 1, 0, minus alpha 1, plus 0, alpha 2, minus alpha 2, equals 0, 0, 0. And the addition, alpha 1, addition, here is second coordinate, second, on the second position we have we have alpha 2. On the third component is minus alpha 1 minus alpha 2. And this is the null vector. The null vector. Two vectors are equal if and only if they have the same components. So from this we can see that alpha 1 equals alpha 2 is 0. From this we get that the considered system of vectors is linearly independent. Now a definition. The definition for the basis, the notion of basis of a vector space. Definition. Definition number I don't know 4. No, the definition. B. Let us denote by B. V1, V2. Vn is a basis of space B if the following two conditions are satisfied. B is a spanning set and B is also a linearly independent system of vectors. So we have two conditions. Firstly, span of B is our space, and this is the first condition, and B is a linearly independent system of vectors. Now let us present the following remark. First, if S, a system of vectors, is a linearly. Let us denote by S, as in the previous cases, a system of vectors from V is linearly independent, then 0 cannot does not belong to S. And the second remark, the null vector space containing just one vector does not admit a basis. As concerns the first statement, we have necessary V1 different from 0. If V1 is 0, then we have the following relation: 1 multiplied by this vector. I can put here V1 plus 0 V2 plus so on plus 0 Vn is 0. So it is possible to have a linear combination with the coefficient equals to 0, with the coefficient different from 0. But this is impossible. Our system of vectors was supposed to be linearly independent. This very, very special vector space does not admit a basis. We have just one vector. So in the case when V is the null space, this is the only vector. In this case, for the only possibility, a non-empty set of vectors to put this, but this is not a basis. B is not linearly independent. B contains the null vector. The other possibility, B equals empty set. This is not a spanning set. Span of this is not. So the null vector space does not admit a basis. An example of basis. The simplest non-trivial example in R2 be formed by the vectors E1 equals 1, 0, E2 equals 0, 1 is a basis, called the canonical basis. They evidently for any x, x1, x2 from R2, we get that x, which is x1, x2, will be a linear combination. It's just x1 E1 plus x2 E2. So we get that R2 is span of B, and these vectors are also linearly independent. If we take a linear combination of these vectors equals to the null vector, then we arrive at the conclusion that all the coefficient must be 0, alpha E1 plus alpha 1 U1 plus alpha equals 0. We get this is exactly alpha 1 alpha 2 equals 0. Here the null vector is this one. We symbolically denote it by 0. So this is 0, 0, and from this we can see that alpha 1 equals alpha 2 is 0. So an example of basis. Now let us prove some results directly related to the presented definitions. Firstly, the following result. If in S, which is the system of vectors V1, V2, Vk, Vn, we keep our notation. If in this Vk is a linear combination of the other vectors, let us write this in the following way: a sum for m from 1, m different from k, beta m, bm, So Vk is a sum of the other vectors from this system. Then span of S is the same as span of S if we eliminate from S this vector Vk. Then the two systems of vectors span the same subspace. Proof. We have to prove that we have here an inequality between two sets. So we use double inclusion. Firstly, this set is evidently contained here. All the vectors from this are here, so it's obvious. Now the converse inclusion. If X belongs to span of S, in this case X will be a linear combination of this. X will be sum for M from 1 up to N alpha M Vm. But we separate here the term containing corresponding to K, so this can be written as sum for M different from K, alpha M Vm, and we have also to add alpha K Vk equals we keep this sum for M different from K alpha M Vm plus, instead of Vk we can put this plus alpha K times sum for M different from K beta M Vm, and this expression can be written as sum for M different from K alpha M plus alpha K beta M Vm. So we get from this that the considered vector belongs to this set to span is a linear combination of the vectors from this set of vectors. Span of S minus Vk. Vk has been eliminated from S. So from a system of vectors, if we eliminate a vector which can be expressed as a linear combination of the other vectors, then the span of S is the same as the span of the obtained set after eliminating a vector which is a linear combination of the other vectors. Now, as concerns the linear independence, a theorem the following result. If we have a set of vectors satisfying the following two conditions: 0 does not belong to S, where S is, we use our notation V1, V2 up to Vn. This is the first condition, the first condition, and the second condition is Vk is not a linear combination of the vectors written before it of V1, V2 up to Vk minus 1. And this happens for any k from the set, for any k from 2 up to n. None of these vectors is a linear combination of the vectors written before it. If these two conditions are satisfied, then S is a system, a linearly independent system. Of vectors. Proof. In order to prove that we use the definition, for this we consider a linear combination as usual. Let alpha 1 be 1 plus alpha n minus 1 Vn minus 1 plus alpha n Vn equals 0. We have to prove that all the coefficients are 0. Let us consider this is the relation star. A first remark is we have alpha n equals 0. Since alpha n different from 0, then from this relation, from the relation star, we get that Vn can be written as a linear combination of the other vectors. Vn will be minus alpha 1 over alpha n. V1 minus so on minus alpha n minus 1 over over alpha n Vn minus 1, but this is not possible. We know that none of these vectors is a linear combination of the vectors. So we know that alpha n must be 0. Now the starting relation star becomes, can be written as, we know that this is 0, 0 multiplied by a vector is 0, so we get alpha 1 V1 plus so on, plus alpha n minus 1 Vn minus 1 equals 0. Exactly in a similar way, we prove that in a similar way. We prove that alpha n minus 1 is 0, and so on. We can continue, and finally the starting relation becomes it remains just this. It becomes alpha 1 V1 equals 0. But V1, the system does not contain the null vectors, so V1 is different from 0. And then from this we get that alpha 1 must be 0, since alpha 1 different from 0. From this we get that V1 is, we can divide this equality by alpha 1. We get 1 over alpha 1 V times 0. And this is 0. We can express from this V1 if we multiply this relation by 1 over alpha 1. So we have these are sufficient conditions in order to have a linearly independent system. Now we use this result in order to prove the following theorem. From any spanning system of a vector space, we can extract a basis. So theorem. If span of S is V, then from S we can extract a basis B over V. From a spanning system we can extract a basis by using the previous result proof. The first step, firstly, we eliminate zero from S if it exists, if there exists, if exists. So the first condition is satisfied. Then we eliminate each vector which is a linear combination of the vectors written before. Then we shall give an example. Then we eliminate each vector Vk, which is a linear combination of the vectors written before, of the vectors before it. After such an elimination, the obtained system is also a spanning system for V. After elimination of such a vector, the obtained system of vectors also spans V. Finally, we get a basis of V. Let us consider an example in order to illustrate more exactly this method to extract a basis from a system of spanning vectors. An example, extract a basis from the system of vectors as the system in R3, V1 equals 1, 2, 3, V2 equals 0, 0, 0, V3 equals 2, 4, 6, V4 equals 1, 1, 1, V5 equals 2, 3, 4, V6 equals 0, 0, 1. Solution. Let us be S0. After the first step, S first by eliminating. We have the null vector V2. We get the system S1, which contains only V1. This was V3, V4, V5, V6. Now, we consider the second vector and we analyze if it is or not a linear combination of the first vector. V3 is this vector. You can see since V3 is 2 times V1. That is a linear combination of a vector written before it. So we eliminate these 3 and arrive at the system S2. We have V1, V4, V5, V6. Now, we use the same method. The second vector is or not a linear combination. V4 is here. No, V4 is not a linear combination of V1. V4 is not a linear combination of V1, so it remains. So at this step, our set remains the same: V1, V4, V5, V6. Now we consider V5. V5 is a linear combination of the previous vectors, since V5, which is V5 is this is V1, V1 plus V4. We eliminate. V5 and we arrive at S23, S4, which contains V1, V4, V6. Here, none of the vectors is a linear combination of the previous. This is a basis. V6 is not a linear combination of V1 and V4. Now, the last theorem. Oh. My computer is in standby. I hope our video clip continues. And the last theorem. Each finite dimensional vector space V, but different from the null space, admit a basis. Finite dimensional means the existence of a finite spanning system, but from such a spanning system we can extract a basis. So this is our video clip. Just a short overview on the presented results. Here is an overview, the definition of the vector space. Here is the definition for okay, it is okay, wait, you can see this. The definition of a subspace. Here are the subspace spanned by a system of vectors. Here are is the theorem S and S minus Vk spans both the V. And here the definition for the linearly independent system of vectors. And here the remark that a system of linearly independent vectors cannot contain zeros, the sufficient condition for linear independence. Here the definition for the notion of basis of a vector space, and from any system of generators we can extract a basis. Any vector space admit a basis. Here is an overview which you can find on my website. This is the address, and here you can find an overview on linear algebra, my book in Romanian, and an introduction to complex analysis, to differential equations, to Fourier analysis, and my notes on the description of quantum systems. Thank you.